Thank you again. So we'll continue with our discussion of deformation. So last lecture towards the end, we mainly talked about Eulerian description, also can be called spatial description and Lagrangian description. Also can be called as material description. So if you have a scalar quantity, I'll call it G with a bar. You can write that as G as a function of x comma t, where x is the position vector of a material point. Okay, actually I shouldn't say material point, I'll just say position vector of a point in space, of a point in space. And t is time. It is also equal to G tilde of x, uppercase x comma t, where x denotes a material particle. X may not be a single point. X could be a bunch of points which represent that material particle. And material particle, the best example that I can think of for you to remember this as you go forward is, I'm just going to write some of this I told last week, which you can also see in the video. Imagine an oil droplet released at a point whose coordinate is x at time 0. Okay, so x here is the location, and suppose we are reading density at x comma t, it refers to the density at that point at a given time. It is pertaining to the density at that point, which may be occupied by the oil droplet or later may be occupied by water, but it is fixated on that point. Okay, when we write rho of x bar comma t, it refers to the density of the oil, which is our material in this case. It refers to the density of the oil. Now at time 0, that oil droplet is occupying a certain point. Now suppose you are interested in the density of whatever resides in that point, and you are following the droplet. If at a later time the droplet goes elsewhere, you stop paying attention to this point and you follow the droplet, whereas you are still looking at this point. If your attention is at a point, is about a point in space, you are doing an Eulerian description. If your attention is about a certain material clump, wherever it goes, however it changes shape, you are doing a Lagrangian description. Remember this. This is the summary of last lecture. Okay. And why we need these two types of description will become apparent as we go. So I'm going to start with figure 3.4. So I must also say the time I allocate to each chapter is going to be highly nonlinear. Like if you think about it, we spent about a month, little over a month for chapter 1. We might spend about a month for chapter 2. and maybe 2 weeks for chapter 3, maybe 1 week for chapter 4. So it will get non-linear in the sense, as we go further, we'll spend lesser time, but the concepts are more built up with the methods from prior chapters. Okay, so don't ask me to spend equal time for every chapter. It won't be like. And I'm taking all my time for these earlier ones because these concepts are very basic. Even outside this course, you will need that. That's why I'm not rushing this. And if I go too fast, stop me. All right. So I have figure 3.4. Let's say this is an axis. I have a certain body or a material whose initial shape is, let's call it V naught. V naught is the initial shape. Okay. And if there is a point, we'll call it P. That point has a reference vector or a position vector. We'll call it X. And this configuration is the reference configuration. Whatever we use as the reference configuration, we'll call it with uppercase letters. That is, think of a shape. Before you do any loading on that, it has a certain shape, and any point on that shape you can denote with a position vector. You call it X. Okay, this is your reference coordinate system or reference configuration. Now, after deformation, suppose that material has a new shape B. B is the current or final, depending on how you see it, final shape, initial or reference. Okay, and that point P, whatever material that you initially considered would have moved on to a different location. Okay, and that has a position vector. We'll call it X. So this point P, its neighborhood points, we'll say dx, and this point P, its neighborhood, we'll say d lowercase. Example to keep in mind is let's say you label a point on a sponge and you're squeezing the sponge, you can see the point move from one location to another. Spatially, you can say that that point has moved by a centimeter or whatever. But if you are sitting on top of the point, you are just part of the material. If you have relocated with respect to that point, if you consider that point itself as the reference, you have not moved, the surroundings have stayed, you have not moved. But if you're seeing this from outside, it's like the point went from one location to another. Okay. So we are going to start description of local deformation. What we at a basic level track, we track the position or shape, actually positions of material particles. Positions alone do not tell anything about changes in length, area, or volume. Using positions, we need expressions for linear area and volumetric strain. Why do we need to worry about linear length change or area change or volume change? When you are doing material testing, you apply a load, you might be doing simple axial loading. In that case, you are interested in length changes, or you might be doing shearing, where in case you are interested in area, how the area deforms, or you might be doing hydrostatic loading or volumetric loading. So it could be like a submarine that is sinking under the ocean under intense pressure. The submarine is getting crushed from all sides by the hydrostatic pressure of water. So you're interested in how much volume will change of that sheet metal used for making the submarine. So we are always interested in changes in length, area, or volume as engineers. That's what we do. The whole idea of deformation is about tracking one of these. So mathematically, you can write an expression that says x equal to phi of x. That math can't get squat done unless you can convert this into a change in length or a change in area or a change in volume. Would you agree with me? It's useless to keep working out with these functions if they can't make predictions that are verifiable in the laboratory. We need mathematics to do that. That's all I'm stating. So how do you go from this deformation mapping to these expressions, which if you divide by the initial length or initial area or initial volume, you call them as strain, area strain or area change or volumetric strain, right? So we are going to, today our goal is to derive expressions for these using the deformation or starting with the deformation mapping. Can I erase this part? So the first of those mathematical quantities that we are going to see, one, actually should say description of local deformation covered in section 3.4 in the book. And we are going for deformation range. F. Now, what is this deformation gradient? So over here, I drew a diagram, right? So let's say I have a point P, which has a position vector x. And when you apply a load on this point, I'm not talking about the entire material, just locally to this point, if I apply any load, that point is going to shift by a certain distance. And this distance could be x plus dx. That is, P dash is the new location in the neighborhood of P. So we say x went to x plus dx. X went to x plus dx. You do have this relation, which we call as deformation mapping. Okay. If instead of passing an argument, instead of instead of x as an argument, suppose we consider x plus dx. That is, in your rubber band experiment, you have a point, you label it as with a marker, call it P or whatever. That point is shifting by a certain length. You consider a point that is very close to P, very, very close to P. That's what we denote by dx, like an infinitesimal separation. How will that neighboring point deform? That is the question here. So if you think x follows this relation, x plus dx should also follow the same relation. It's easy for us to imagine linear relationships. Like when you think of a rubber band, you think that every point in that line is deforming by the same amount. So that if one moves 1 centimeter, its neighbor also moves 1 centimeter. It's linear. But not everything is linear, right? Sometimes you get behavior that is very different at different locations in a material. Can you give an example of that, something that behaves non-linear? It'll be easier to connect if you think physically first, then before doing math. Non-linear behavior in materials. Squeezing of a sponge, can you elaborate, please? Good. So you are saying that this mapping is working differently at different positions. So you might have something that is non-linear dependent on how far you are. Okay. So if we write x plus dx is equal to p of x, or I'm going to write this is equal to p of x plus dx. And I can write this as p of x plus a correction term. Before you write this, in calculus, you've always thought of a small change in the input leads to a change in output. That is, if you know, for example, y is a function of x, you can write y plus dy equal to f of x plus dx, which is often written as f of x plus dy by dx times dx or delta x. Yeah, I'll write it as dx. Plus, you can write d squared y over dx squared times dx squared plus d cube y over dx cube, and so on up to infinity. This relationship is famously called Taylor's series. It basically reconstructs a function in terms of its value at a point and the nearest and the slope, curvature, third derivative, fourth derivative, and it becomes more exact as you add more derivatives. But if you just stick to very short, very small values of dx, you can get away with by discarding all of these higher order terms and approximate this function using only its slope and the change in x value. Maybe I'm not making this very clear. Suppose you have a function x, y. If I make a small change in x, I want to know how much will my function change. If that is my question, what I would do is this curve might have some true behavior that may look like this. At this point, if I just locally compute the slope, okay, if I take the slope and multiply it with delta x, this value here, I will get an approximation for y that may or may not be the true value. If the underlying function which you don't know happens to be a straight line, then this approximation is exact. If your function is perfectly linear. But if the underlying function were nonlinear, if you make this delta x smaller and smaller, your approximation gets better and better. Because in a very short interval, any curve can be approximated as a straight line, even if it is not really a straight line. This is the basic idea. When we apply that to a function whose arguments are not a scalar, it's not x, it is x as a vector, then we need to think about a correction term which involves the slope multiplied by dx. Am I making myself clear at this point that you need a linear correction term which is a derivative of phi, multiplied by the change in x itself? Is that getting through to you? So this slope here would have to be a derivative of phi with respect to x. Okay, but phi itself is equal to the position vector in the spatial coordinate. So we write this is partial x with respect to uppercase x. Before you tell me or do anything, what kind of a quantity is this expression? Derivative of a vector with respect to a vector. We saw something like this in the first unit. Can you tell me, is this a vector? Is this a scalar? Is this a tensor? If tensor, what order? Is the vector? Your answer is vector, you're saying. Okay. Anybody else wants to say anything else before I go a little bit into this? Okay, we have one response, which is vector. Let's think a little bit here. Okay. So this is partial phi over partial x at x multiplied by dx plus higher order terms which we neglect. I'll leave it at that. Let's come back to this. Answer these questions for me. What is x? What is uppercase x? Are they measured with respect to the same coordinate system? Answer these three questions for me, please. What is x? What is uppercase x? So remember, when you are talking about uppercase x, you are measuring it with respect to a body whose shape hasn't changed yet, and you call it a reference. Okay. When the same point at a later time after it has been deformed, you refer it to a position vector x. That position vector is not defined with respect to the initial basis. Basis meaning initial coordinate system. Why? So let me help you recollect one thing I said in the first unit. For any given shape, a natural coordinate system always comes from its eigenvectors. Okay, you can take any shape or any a shape which has certain symmetry. Suppose you are talking about the torsion of a cylinder, it's most convenient to use a cylindrical coordinate system for the reference configuration. But after you have twisted it or deformed it and done some operation on that, that coordinate system may not be the most natural anymore because it doesn't have possess that symmetry with which you began. At that point, you might have a different way of defining a coordinate system for that shape. And with that coordinate system, you will have a position vector. See, we are thinking about deformation in just binary terms. There is a reference shape. It has its own coordinate system to describe it. And then there is another state, which is now after deformation. It has its own coordinate system to define it. So there are two coordinate systems here. Each configuration, both the reference as well as the current or final, have their own coordinate systems. Is that something you could see or agree with?
Yeah, but can you maybe explain why? When you have to change the coordinate system? You have to always change the coordinate?
You don't have to always change the coordinate system, but every shape has certain coordinate systems which make it natural to describe it. So if you are suppose taking a deformation, which is pure rotation, all I'm going to do is I take my marker. My marker is initially pointed vertical. I'm going to rotate it 90 degrees towards me. It's not really technically a deformation. It's more like an orientation change. It's just going from like this to this. So in this scenario, I can describe the initial position as E3 cap. Final position is minus E1 cap. Same coordinate system, I'm able to describe both the reference as well as the final configuration. But if I started like this, I'm not only doing this, while I'm doing this, I'm also twisting and bending it. So it's rotation, torsion, bending. So at that stage, this cylinder has lost all of its cylindrical symmetry. It might be better to have a different coordinate system to describe it. So I'm abandoning the reference. I'm sorry, I'm abandoning the coordinate system used for the reference, and I'm having a separate coordinate system for the current. So the key thing I'm trying to tell is X and uppercase X are generally defined with separate vectors as basis vectors. So we can write X is equal to Xi EI, where E1, E2, E3 are the basis vectors. And we can also write X equal to Xi EI uppercase, where E1, E2, E3, and there should be a better way to do this because somehow the book keeps using this I. That's why I also need to use the I. So I won't write E1, E2, E3. I'll write EI, where I runs from 1 to 3 is the spatial coordinate system, and EI uppercase, where I runs from 1 to 3 is the material coordinate system. I'll give you another example. we'll come back to our oil droplets. Okay, so I have a rectangular tank, and I'm putting my droplet at a certain point in space. I can denote the position of that point as x1, y1, z1 because that is a rectangular tank. I'm just going to use a Cartesian coordinate system, and I can tell the initial position is -2, 4, 5. That's 3 coordinates. Okay. This describes where my droplet is. Okay. That droplet size may be 4 units of radius. So just to keep it organized, let's say I have a Cartesian coordinate system. I have the initial location of my droplet. And this droplet has a radius. We'll call that radius R0. Okay. And if you ask me, what is the density at this point P, which is given at position P, all I have to do is at that time, whatever material is located at point X, lowercase, I need to get its density, and it might be the density of oil. Okay. Now, if this droplet, let's say we apply force and squeeze it and turn it into something that looks like a disc. Okay, it has deformed. To express the extent or the deformation of this droplet, it doesn't make sense anymore to describe what is going on here. I have to describe what is going on wherever the droplet still can be found. So if I define for this pancake a coordinate system, okay, a coordinate system which is centered at the droplet itself, and in that coordinate system, I have x1 squared plus x2 squared plus x3 squared divided by a squared plus b squared plus c squared equal to 1, to denote that the shape of this droplet is like an ellipsoid. So I have one coordinate system which is related to the space, and one coordinate system which is related to the material. If the shape of the droplet changes into a cylinder, I might go for a different way of representing this, but these two are distinct coordinate systems. That is what I'm trying to illustrate here. Okay, so this has basis vectors. We'll call it E1, E2, E3. This has its own basis vectors. To distinguish, I'll call it E1 prime, E2 prime, and E3 prime, which may or may not be same as E1, E2, E3. So in that first example I gave, if all I'm doing is moving the droplets around, I can just use the same basis vectors. But if I'm also deforming, it would be better to define its own coordinate system. Okay, so this distinction will become apparent when we look at some specific examples for this deformation gradient. Last lecture we saw an example, right? X1 equal to or x equal to alpha x. This is the example we saw last week. A uniform stretching across every axis. So in that example, it's easy if you define both using the same coordinate system because it's just stretching. In some other example, we may have different coordinate systems for them. So we generally think xi or x is xi ei, and x is uppercase x is xi ei uppercase to denote it is a material coordinate system. Okay. Is it making sense, or you're still not very sure? If you have a question, please ask. But this is an important idea. I don't want to push this through. Okay, I'll try just one last thing. This dx, you can think of it as the change in position, or sorry, not change in position. It is the location of a point near your current position. That is x plus dx. X plus dx uppercase. Firstly, let's start by recalling what is x. Is it the position of a point? It is a position of the, if it is the positions occupied by a material point. If that material, sorry, it's the position occupied by a material particle. If the particle moves to the next location, that is what x is denoting. X is not localized to a certain location in space. That is what lowercase x. Remember my example, one is focusing on a point in space, whereas the other is tracking a material moving through space. So wherever that material is, that is x. Wherever that point is, that is lowercase x. Okay. So this dx, what will be then dx? If x is the location of a material particle, what is dx physically? This is easy to interpret. Lowercase dx is just the neighboring point. If this point is x, then the neighboring point is dx. It's easy to say. But what is dx uppercase?
Material adjacent to it, particle next to it.
You could interpret it as, if x denotes the location of the material particle, dx is sort of the change in length of that material particle. Initially, you are occupying a point, or you are occupying a bunch of points. Now you are occupying that or something more than that. That could be interpreted as a change in your length. Change could also be a negative change, so it could be a contraction or an expansion. So you can think of x plus dx as a change in the material's physical dimension, or okay. Coming back to my droplet example, if I had my droplet at a certain point, and the droplet is a sphere initially, let's say it has a radius of 1 unit. Can you tell me, in terms of this basis here, E1, E2, E3, what is the x lowercase denotes exactly this one point? What does x uppercase denote by my definition? X uppercase is basically the volume of the droplet. Wherever this droplet is, it is all x. So x really varies from wherever the droplet is. If the droplet's shape changes, then x is now here also. Whereas this x is always about the center of the droplet. Even if there were no droplet there, it is still the address of that point. Whereas x kind of describes wherever the material is, or whatever the shape of that material is. So once it has become flattened like a pancake, okay, first, before the deformation, when the droplet is still spherical, can you tell me what is x uppercase?
It's the volume.
It's the collection of the points that make up that sphere. Whatever region is within the sphere. So if the sphere is, for example, before deformation, x represents all the points which are x minus a squared Or right, x minus x naught squared plus y minus y naught squared plus z minus z naught squared equal to r naught squared. X is all these points, x uppercase is all the points which are within the initial sphere. When the initial sphere becomes a disk after deformation, X still denotes the particle, but it denotes all the points which are now moved away. So X here is clearly a function of lowercase x. It is defined by that one attribute. If there is a material particle at that point, it counts under X. If there is no material particle at that point, X is not defined there. This is what I meant the other day also about territory. Like if you say that this territory belongs to a country, then that country exists there. If that territory belongs to somebody else, then that country doesn't exist. That's what X is. Okay. So coming back to my question, X is a vector defined with spatial coordinates, and uppercase X is a vector defined with material coordinates. So this quantity is nothing but xi ei partial derivative xj ej. I'm going to erase all this and write this clearly. X equal to phi of x. This is what we start with as deformation mapping. This is equivalent to writing xi ei cap equal to phi of x or xj ej. We write x plus dx is equal to phi of x plus d uppercase x, which by Taylor's series is p of x plus partial phi over partial x at a given position multiplied by dx. Partial phi over partial x. Or I'll write from this equation, I can write x plus dx equal to, this is same as x, so you have dx equal to partial phi over partial x at x multiplied by dx. Okay. What is dx? Dx is dxi ei or this is dxi times ei, and this quantity here, the right side, partial phi over partial x at x times dx. This is equal to partial phi over partial xj times dxj. In other words, what I'm writing is combining these two. I'm going to write dxi is equal to partial phi over partial xj dxj, and phi or phi is nothing but uh, phi is nothing but, hold on. Combining these two, I'm going to write dxi ei cap equal to partial phi over partial xj dxj. This is partial of xi ei over xj dxj, which is partial xi over xj uppercase dxj ei cap. So I'm allowed to compare this coefficient with this and write dxi equal to partial xi over partial xj dxj. This series of steps, did it make sense to you? Did I go over something too fast? Up to this, we discussed qualitatively. This step here is just writing out x as a vector and substituting for the fact that phi is nothing but x, or phi is a function that relates x and uppercase x, so that I can write the change in x is the change in x with respect to each direction multiplied by the change in that direction. And this quantity here, it depends on xi and uppercase xj. It is a mixed, it's called, it is a mixed order tensor. It's a mixed order tensor. So dxi equal to partial xi over partial xj dxj. If you look at partial xi over partial xj is a mixed order tensor with a dyad which is ei and ej uppercase. So it's like taking one direction from one coordinate system and another direction from another coordinate system and defining a dyad with that. Usually you are used to seeing E1 E1 or E1 E2, which are part of the same basis vector, same three coordinate system. E1 is one direction, E2 is one direction. Here it's like saying we'll take one direction from the spatial coordinate system, one from the material coordinate system, and define this tensor. That sounds a little unsettling, but more importantly, you look at this expression and can you kindly interpret this for me? Look at it, explain to me in words what this expression means on the left side and on the right side. What is dx uppercase? What is dx lowercase? Can you talk about it? dxi is easier to interpret. What is dxi? Change in position.
Yeah. Infinitesimally
Change in position along the direction I. So the way to think about it is, you take a material particle, you can monitor it from two frames of reference. You can be fixated on a position in space, or you can be fixated on the material itself and how it's deforming. If you say that this dx uppercase, it's easier to interpret in my mind. It's like saying my material particles initial length along direction j is x, or initial position is xj, and it has changed by a length dxj. It's the actual change in length of the material. Okay, it's the actual change in length of the material. But when you see it from a spatial coordinate system, that is, when you see it from a frame of reference that is outside the material, that change in length may not be what you observe.
like change in length as in from one side of the material to the other. Or change.
Okay, change in length is what is happening in the material. When you see it from outside, you don't see it as a change in length, you see it as a change in position. This is change in position, this is change in length. There is a difference between the two of them. Are we able to see that difference? Change in length is not same as change in position. Because you may not do everything in a straight line. Maybe you had a loading that is along this axis. Maybe you have a load that is also pulling it down. So think of your rubber band. If you are going to just go back and forth, it's almost like saying change in length and change in position are really the same thing. But suppose I have this force acting on the rubber band and I'm also pulling it transverse direction. So this point that you label is not just going to the right, it's also going down because I'm also pulling it down. So if you just think I will stand outside and measure the change in x coordinate, you're going to be fooled because it's not only moving along x, a part of component of the motion is also along the y direction. So change in position is not just change in length, it is multiplied by the rate at which this gradient is happening. So as most loading scenarios are multi-axial or multi-dimensional, it is improper to think a change in length in the material is the same as change in position of 2 points. That is what this relationship shows. This quantity here, we'll call it Fij, J uppercase. Fij is the deformation tensor that measures the rate of change in spatial position or position with respect to the location of a material point. The material point will keep moving. That droplet originally was at one location. It got flattened. Maybe it got separated into two droplets. Maybe it's no longer at that point where you released it. It will keep on changing its position. This, if you're all about just monitoring what happens here and here, is there a droplet here? Is there a droplet here? Sometimes the answer to that question is no, there is no droplet at those 2 points because the droplet has gone somewhere else. So dxj is the change in length of the material point and its neighborhood. dxi is the change in position with respect to a spatial coordinate system. And Fij equal to partial xi over partial xj connects the two. And how do we know Fixj or sorry Fij? Fij is nothing but the deformation mapping in tensor form. Ooh, this sounds revolutionary. It's nothing but the deformation mapping. Is it really? So last lecture we talked about different examples. One of them is x1 equal to alpha x1 plus x1 plus gamma x2 and x2 equal to x2, x3 equal to x3. Can you obtain Fij from here? Fij is partial xi over partial xj. What is F11? That would be partial x1 over x1 uppercase, which is 1. What is F12? Partial x1 over x2. What will that be? How did I write this is 1 by the way? So in general, x1, x2, x3 are independent of x1, x2, x3. So when I write partial x1 over x1, I'm writing partial over x1, x1 plus gamma x2, which is 1, because the second term is 0. So this is 1. By the same logic, this is gamma. And you can write f as a tensor, which is Fij, Ei, Ej equal to 1 gamma 0, 0, 0, 1, 0, 0, 0, 1. So this is your deformation tensor for a very simple deformation here. Again, we construct this deformation tensor because I told you this dxj is the real deal. It's the change in length. Physically, what do you care about? You care about real deformations, not what your perception tells you, which is the lowercase dxi. So if you want to get area change or length change or volume change, you have to use this expression to get those changes. So if your area change, if your length changes by dxj, how much does your area change? That's the question. Or how much does your volume change? Okay. So how do you obtain deformation gradient? Quick recap. So if the deformation mapping x equal to p of x is known, then f is calculated as Fij equal to partial xi over partial xj. Okay, we are going to do, I mean, you can, I'll post the second homework, or maybe I already have, I'll go check. But if you look at the end of the chapter, I'll suggest some problems here. Let's try problem 3.1. X1 equal to uppercase X1 plus A X2 plus B X3. X2 equal to X2 plus CX1 plus D X3, and X3 is simply X3. Simple example, compute the deformation tensor for this transformation. Now it's now math, it's just math. We give you a transformation or deformation and ask you to compute f. It's just getting derivatives of x1 with respect to this, and this. So this deformation tensor will look like 1ab C1d 0, 0, 1. If you ask me, why do I put up with this deformation tensor? Because it gives me a pathway to compute the quantities that an engineer would care about, such as change in length, change in volume, or change in area. This relation is written in terms of dxi in partial derivative of xi with respect to uppercase xj dxj. It's not giving me what I want. What I want is this quantity, dx vector or dxi. This is what I want, but that's not given here. How do I get this? First question for you. So if this is Fij, can I write dx vector is F tensor, dx vector is F as a tensor dot dx vector. Can I write this? Right? Can I write this? Yeah. So now if I multiply both sides by the inverse of f dot dx equal to f inverse multiplied by f dot dx. What is inverse multiplied with its own tensor? I. I saw you saying I. So this is the unit tensor dot dx, which is nothing but dx. you can do it both ways. You can specify the tensor from which you can get the true displacement. Sorry, from which you can get the change in position, or from its inverse, obtain the true displacement. Remember this, when you are doing an experiment, which coordinate frame are you really using? Is it the spatial or the material? Why? Correct, and why?
Because we can't look at every little particle most of the time, and so we can't track every particle.
We cannot track every particle most commonly. The other is, by definition, we are in the laboratory. We are putting a strain gauge and measuring the local strain at certain positions in the material. So if you are taking a big block of sheet metal and you put strain gauges everywhere, it's the equivalent of doing measurements at each location. The strain gauge will tell you the change in length in that location. So this quantity, the left side, is what you commonly measure, but for your analysis, this quantity dx uppercase is what you really need, because that is the true change in length. Okay, so we often measure this, and if we know the nature of the deformation, we can obtain the true deformation. Okay, once you have the true deformation, this is nothing but change in length. Change in length. Right? Dx vector is nothing but change in length in each direction. And if it's only along one axis, it's just dx I cap, or along one direction. What else do we want to know? Area change, volume change, right? We want to also know those quantities. So the general principle is, I'm going to just say that first before I work out those quantities. Say, think of, you have a unit cube. We are going to often invoke the unit cube. E1, E2, E3. Okay. Now, if your deformation, or your the change you are applying to this volume, you might call this the reference configuration. So in your reference configuration, suppose you take this area dA naught. Area is treated as a vector whose magnitude is the magnitude of the area multiplied by the normal vector that is perpendicular to the area. N cap. N cap. So this is the initial area. You have some area element. I just drew it for simplicity to imagine that it is along the 3-axis. It can be any area. It can be something that is arbitrary dA naught multiplied by n cap. Okay. The question is, what is the change in area, or how is the change in area related to the original area? That is, you apply a shear deformation or twisting or bending or something, that something is contained in the deformation tensor. That something is contained in the deformation mapping from which the deformation tensor is computed. So the question is not how can you do a certain deformation. The question is, if you do a certain deformation, how will my length, area, and volume change? How can I relate the initial area to the area after I have done some really funky twisting, turning, and everything? How can I go from map this area to that? That is the question. Okay. So this as well as writing what is my change in volume in relation to the initial volume. These two are the two important other questions which we will answer. Hint is both involve operations on the deformation tensor F. And since we are about 5 minutes out, I don't want to start now. I would like you to just review 3.4, 3.4.1, 3.4.2, 3.4.3. Review these by Tuesday's lecture. Okay. Also, by Sunday, I hope to post a mock exam for the upcoming exam, something that is to give you a sense of what is the format. It's 4 questions, one question and 3 problems, and the time it might take you to solve them. So it's 80 minutes, 4 questions. I try to choose the problem such that it takes about 20 minutes per question, per problem. So it will give you a sense of the exam, which I hope to post by Sunday. Okay, so that you will have some time to look at it. And please, next week, if you need to speak with me, come and talk, send me an email. I'll be in my office. Let's make sure that you are well prepared. Okay.
Are you gonna be strict about the time, 80 minutes?
Yeah, that's what that's why I say 80 minutes. Otherwise, I say whatever you please. Yeah, we start at 5:30, we end at 6:50. You are allowed to access any materials. How much more lenient can I get?
Some professors.
No, 80 minutes. Yeah. By Sunday, I'll post 1 mock exam.
Can you bring that?
It's a lot more work to come up with the answers than just question. I'll try. If you are not able to solve something, I encourage you to come and talk to me, show me your work so we can discuss. I generally don't want to post a solution. Okay. Yeah, because yeah, I don't want to. All right. Thank you.